Okay, so nobody's here today, but that's all right. We'll move forward. And just a couple of announcements first, I guess. I will try, let me rephrase that. I'll have your guys' exam graded by Tuesday is my target date. I try to get it done within 1 week of taking the exam. In addition, all of your homeworks hopefully will be graded by the end of next week so that you know where you stand. I'll get the labs done before the weekend, I think, and then I'll get everything caught up so you can see where everything's at. But yeah, expect me to catch up on grading here. I've fallen behind. I'll get caught up for you guys. Also, when I was going back through, so I started grading, I have a couple different classes. I got caught up on one of them. You guys is kind of next in the queue. What I noticed a couple of mistakes that I made in the homework solutions. And this is the first time that I've used these homework questions. So I'm gonna be a little more prone to making these mistakes. So for the first person that comes to me with the correct solution, I'll give them some extra credit points. So if I post solutions and they're wrong and you let me know with what the right answer is, I'll give you some extra credit points on that associated homework. So that everybody can get the right answer, because like one of the examples was, there was a question on how many transistors does this circuit take? And I had the right number of transistors per gate because it was like XOR gates, but I had the wrong number of XOR gates. It was like 2 XOR gates and I counted 3 or something like that when I drew the circuit. So it was just like a little mistake, but I want to make sure those get caught so you guys don't study the wrong stuff. All right, so today I'm going to be going over what we would just call combinational logic devices and kind of talk about them, I don't know if more in depth is right, but I've tried to sneak a lot of the material in that we're talking today earlier. So this is hopefully kind of like redundant repeats. So the first thing that we'll talk about is full adders and half adders, right? So we talked about addition, adding circuits, and the difference being only that a full adder has a carry in and a half adder doesn't. It only has the carry out, right? Where the idea being that just like in decimal, I don't have to worry about how to add this whole number to this whole number. I can worry about it one column at a time, right? So 1 plus 1 is 0 with the carry. And then up here, 0 with the carry, 0 with the carry, right? That's how the addition works. The half adder functions for one column, but it doesn't work after that. The half adder, right, we could just draw the truth table. It has inputs A and B and do 2 different outputs, sum and CO, and they end up looking something like this is sum. And the carry out is really just an AND gate between A and B, right? Nice, simple circuit. It's easy enough that you could probably just draw that circuit without even bothering to a K-map or any other sort of simplification. Now the full adder, right, gets a little bit more complicated in that we have to deal with the carry in, so it's a 3 input, right? So we have 8 rows of the truth table. One implementation of this circuit looks like this. Where sum is A XOR B XOR Cn, right? Remember that derivation from last time? And then the easiest way, if I'm using the XOR architecture for carry out, is I really just need to worry about the A XOR B, because that's going to generate Oh wait, I'm gonna skip a tier here if I do it that way. So A XOR B ANDed with carry in, or if I have just A and B. So in either of those cases, I'm going to have a carry out, right? So that's the XOR architecture for this. So
I have a quick question.
yeah,
How does AB and the half adder and then AB and carry in relate with the addition problem you have written, or does it?
yes. So in this circuit, this first column is a half adder because there's no possible carry in the first column. The rest of these have the A vector is this one. Let me actually use colors so that's a little bit easier. So this is A. And then this is B. So I write that. So for this column, I could write A at location 0 plus B at location 0. So that's this A, that B. Now the second column is going to take A at 1 and B at location 1 and the half adder carry. So the carry in from column 1, the first column. So that's what this is. So if I was going right to left, it's A0, B0, A1, B1, and then this it would actually be labeled as CO1, right? Because we're carrying in from the first column, and then I would cascade that. So then if I wanted to draw this circuit, so if I wanted to have a ability to add 3 bits, I could just take a half adder, full adder, full adder, and then this one has A0, B0. So this is what we call the block diagram of a ripple carry adder. So this is where I was going next with this, where it has a carry out that goes to the next one's carry in, and then it has A1, B1, and the sum at 0 we can pull out here. This outputs sum at 1, this outputs sum at 2, carry out, carry in. The carry out, let me make sure I'm still on screen. Yep, the carry out of the last full adder then is the final sum bit. So that gets used 2 different ways. One way is we just call it the overflow. It just carries an overflow flag saying we added up to too big of a number to store in 3 bits. The other way is we can consider it as the 4th bit of the sum from 2 3-bit numbers, right? Because if we add 2 3 bits, I can end up with 4. I won't end up with 5 bits ever. So depending how I designed my architecture for my circuit, I may or may not be able to save that most significant bit, the S3. A2, B2. So this half adder, if all I had was full adders, say I had little integrated circuits, right, the little black chips of full adders, and I had no half adders, a half adder is equivalent to using a full adder where I take the carry in and just tie it to ground or 0. Because if my carry in is always 0, then I only use half of the truth table, therefore it's a half adder. Right, that's all that's saying, is if carry in is always 0, it's a half adder. So I could use 3 full adders and just tie the first one to ground, and it would work just fine. So this then builds up to a ripple carry adder. what does it mean? Well, ripple carry means the carries ripple through the circuit. So on the exam, I had you guys draw a timing diagram, right, for one of the problems. That timing diagram doesn't have any of what we call gate delays. What that means is it takes some effort, some time to change from a 0 to a 1. So if we look at this, and a simple but kind of bad way of doing gate delays is you would just in your technology estimate how long does it take for these to switch. And let's just say that every gate takes 10 nanoseconds. Now that's not really a good estimate because like an inverter is way faster than an XOR gate. Those are kind of extreme ends. The reason being that each of these transistors that you build a circuit on have capacitance. And capacitance is kind of like weight. It's how hard is it to move that voltage. And so when I have lots of transistors, it's slower to move. And when I have fewer transistors, it's faster to move. It's easier, right? So like if I want to pick up this book, I can just pick it up and throw it across the room. But if I want to pick up and move the table across the room, I would need some help, right? So the gate delays, if we do the simple but bad version and just say they're all 10 nanoseconds. Well, then in order to get my first carry out in this architecture, I have 10 nanoseconds plus 10 nanoseconds plus 10 nanoseconds. So what I'm looking for is the longest path. In this case, 3 gates or 3 gate delays. So the first carry out doesn't get generated until I've waited 30 nanoseconds. And now if I do that over and over and over again, well, like this carry out is going to this carry in, and then I have A, B. So I've got potentially 3 gate delays, potentially, maybe as few as 2 if it's just there. So let's call it 3. 3 gate delays for every carry out. So now my delay is 30 nanoseconds plus 30 nanoseconds plus 30 nanoseconds. And now what that means is I can't calculate the sum 3, the most significant bit, faster than 90 nanoseconds. That means I can't create a new addition until I've waited 90 nanoseconds. I've now created a limit on how fast my circuit can go. Well, 90 nanoseconds is kind of long. It's not awful, but it's kind of long. But what happens then if that is a 32-bit addition, which is perfectly reasonable, right? 32 bits, I mean, your operating systems are 64-bit operating systems, right? So it's 64 bits. If they want to do an addition using a ripple carry adder, it would be 64 times 3 gates per bit times 10 nanoseconds, which is a pretty big number actually as far as speed goes. So these ripple carry adders are not fast. In fact, they're quite slow. And later we'll deal with, and I'm not sure if it will be in this class or if you'll have to wait till 3610. It just kind of depends how much material it is. We'll deal with how do we speed this up, because this is not really acceptable for modern high-speed circuits. So there are solutions to this, and as you may suspect, right, we're in engineering, so it's trade-offs. We can make this go faster at the expense of cost or size or complexity, right? And we'll get there. But for now, understand this is called a ripple carry adder. Its main deficit is it is not fast and it doesn't scale very well. We will be building a ripple carry adder in your lab next week. So I'm not going to go much more into depth of this so you can kind of build this, and it's going to be in VHDL. So you'll be using multiple instantiations of a full adder in order to build a ripple carry. And then we'll simulate it and make sure that it's adding the way we expect it to. Okay. Okay, so the next one we've used a lot. Now, the reason we use a lot is because it's important and it confuses students. Is the MUX, multiplexer. It takes two inputs, A, B, well, three inputs really, A, B, and S, or select. Where C is equal to A when select is 0, and is equal to B when select is 1. It's just directing the flow of data. It's choosing where the data is coming from. So what we want to do is, what if I want a 4-to-1 MUX? Well, there's two ways I can do this. The first way is I could drop the truth table. I have well, let me do it this way. Yeah, that's A, B, C, D, select 0, select 1. I output F, and I draw out the truth table, and I basically say, well, depending on what select 0 and select 1 are, F is equal to A, B, C, or D, right? So if select is 0, 0, well then 0, 0 means I want A, so F is 0. So in the case of this one, if select, select was 0, 0, it's still 0 because it's still A. But if select was 1, 1, then it's 1, right? Because D is 1, select is 1, 1, so I take D. The way this looks, if I look it apart, is A, B, C, D, S0, S1. And F, right? That's how I would draw this. But we can do this smarter. So just like that full adder, where I wanted a 3-bit adder, I just used multiple instances of the full adders. We call this design reuse, where we want to reuse the same thing as much as we can because it saves us effort. So let's say I have a 2-input AND gate. Say I have a bunch of 2-input AND gates. How do I make a 4-input AND gate if all I have is 2-input AND gates?
Take another AND gate below it and try to two ANDs together.
What do I time together with?
Get another AND gate.
Perfect. There, 4-input AND gate from nothing but 2-input AND gates. Right? Now I could draw this as a schematic symbol. Now we know what's inside of this is really just 2-input AND gates, but I could draw it like this. How would I build a 16-input AND gate?
Just 8-input AND gates together, or just all the way down.
Yeah, so another way of saying that is 4-input AND gates into another 4-input AND gate, right? So 4, 4, 4, ANDed together, 4, output F, 16. All right, let's apply the same logic. 4-input AND gate, or MUX. Design, reuse. Boom, okay. Now, one last question though. What do we do with the selects? We know we need a select 0 and select 1. Right? Where do they go? How do I order these in order to make them work?
You tie the 2 selects from the first pair of gates to one of the, probably it's 0.
And then this one, S1. So, absolute right idea. Let's make sure it works. So if I set 0, 0, then I'm going to get 0 here, right? 0, 0. A flows to here, A flows to F, F is equal to A, perfect. 0, 1, 0, both of these are on 0, so I have A or C, and then 1. Well, then I have the issue of actually 0, 1 becomes C. So don't feel bad, I actually made this mistake in my last class when I did it. So we actually want to flip them around to S0, S1. That way, when I do 0, 0, 0, 1, right? So then if I have 0, 1, where S1 is 1, then I would get B here because S1 is 1, and then still 0 on the F. Now, you can actually make it work that way just fine, just depending how you define your select inputs. So if you're doing that, just be aware, just do this kind of thing where I go, okay, if it's 0, 0, then I get an A, and then C, and then A gets there, right? And I can do that kind of markup flow that I taught you for other circuits and make sure that it makes sense for what you want. Well, now it turns out you can actually design really complicated circuits using nothing but multiplexers. The book has a whole 2 sections or something on designing circuits with nothing but muxes. We're not going to cover that, but I want you to be aware that it exists. And part of this comes down to being cheap. It turns out that muxes are kind of big circuits, but if you have a chip, an integrated circuit that has nothing but muxes on it, it's easy to manufacture, easy and predictable and cheap. So while it ends up being a little bit big, it ends up being affordable. So there are reasons that you would want to use a mux-based design. We're not going to cover that. I just want you to be aware it exists. Once you have a 4-input mux, you could extrapolate that to a 16-input mux pretty easily, right? Same way we did the AND gate. You can do the same thing with OR gates. If you're careful, you can do it with like XOR gates. All right. So we talked about, if you recall, different ways to implement muxes in VHDL. It was a long time ago. I do have the mux implementations posted onto a file in Canvas under notes. So you can go back and look at those if you want to review that. Next device. There is a device that we call a decoder. Now, obviously, if I'm trying to decode something, there's something called an encoder, right? But almost every book ever deals with decoders first, so we'll stick with that. So what a decoder does is it takes a binary input, usually, and outputs what we call a one-hot output. So another way of saying it takes n inputs and outputs 2 to the n potential outputs. So this type of decoder, let me see if I can find a better black. This one's running a little low. Okay, I'm just going to use D for decoder. And let's say we're going to do 2 to the n is 4. So we're going to take 2 bits, A0, A1, and output F0, F1, F2, F3. Potential 4 bits of output. Now, strictly speaking, a decoder must be what we call one hot. What that means is one wire, exactly one wire, no more, no less, is on, based on the binary inputs. So let's look at that truth table. I have A1, A0, F, 0, F1, F2, F3. And it just says one of those outputs is going to be high. Well, for 0, 0, it's F0. For 0, 1, it's F1. 1, 0 is F2, right? We're just counting up in binary. And then I can go back in and fill in all of those zeros. So this is saying that based on some code, I'm going to output one hot, one of my rows. Now this seems kind of weird and arbitrary, but I am going to give you like a real world example of why we do this in just a minute. But first, let's talk about design reuse. So first off, a lot of times decoders will have what's called an enable signal. In fact, not just decoders, most digital circuits we tend to design with enable. The benefit of the enable is we can turn them on or off to conserve power or prevent them from functioning if we don't want them to. Well, if we do the same type of thing and take a decoder, I can now do a 4 input, A2, A3, now I have 4 inputs to 8 outputs. But if I have 4, I would need 16. So let's reduce this to, well, let me see which example I decided to go with on this one. Right, okay, so let's do a 3 input. So one way that you could do this is, so we're gonna have 3 bits here. And what I'm gonna do is I'm going to reuse A0 and A1 on this guy. And then A2, the third bit, is either going to go into this enable or this enable. Because I only want one of these decoders turned on at a time, right? Because I want only one hot. So to have a, changing this from 2 to 4, we're going 3 to 8. Okay, so how do I make sure that only one of these outputs is true? Well, I just invert the enable. And so if it's 0, I want this to be enabled, the first one, right? Because if it's 0, 0, 0, I want F0. So invert A2 and then feed it into the enable. Okay, so if I have 0, 0, 0, well then this enable is on and this enable is off, and I get F0. Conversely, if I get 1, 0, 0, well 1 means this enable is off and this enable is on, and I still have A0 and A1 are 0, so 0, 0, and I get what I'll call F4, right? There we go. So now I have a 3 to 8 decoder that is using this idea of design reuse, right? I just used what I had, added a couple little circuits, literally one inverter. Now this one has a little bit of a problem. In that I have lost my ability to enable or disable the whole circuit, right? I can't turn off the 8 to 1 because I always have one or the other of them is on. So let's say we want to preserve our enable. Well, then all we have to do is use some AND gates, actually, 2 AND gates. So same kind of thing, we're still going to have A2, but we're going to have an enable signal. So kind of a 4th bit, a 4th input. And then I'm still going to invert the A2, but I'm going to throw it into an AND gate with the enable. Great, right? Because this way, if A2 is 0 and enable is on, I get F0. If enable is off, I get nothing. I can do the same thing down here, where in this case, it's just enable and A2. So now I've preserved my enable for the whole circuit, while also design reusing these two decoders that are one hot. I have a 3 to 8 with an enable. Great. And then it doesn't take too much imagination how to extract this into a 6 to 2 to the 6, right? Okay. So I promised a real world example. And I also need to introduce a new topic. So I'll probably bring this up again later to reintroduce the idea. But it's an extremely helpful idea, and it's called addressable memory. So what is addressable memory? So let's say that you need to store information to use later. A common reason to do something like this is in my 3610 class, I'm going to have you guys build a waveform generator, which means it can generate a electric signal. And let's say that it wants to be a sine wave. Well, realistically, in digital circuits, we can't do this sine wave because this sine wave is analog, right? This is true, it has some value assigned to it down to the molecular level, right? There are all possible values. If this is 0 and this is 1, there are all possible values between 0 and 1. Whereas with a digital signal, if I did that same sine wave, right, it's going to do something like that, where it wants to be a sine wave, but it doesn't have the availability of all possible values. It has some number of bits. Well, let's say that it is a 6-bit number, and I want to store it in memory to be played back later, kind of like a video clip, but with an electric signal. Well, same thing, really. But how do I do that? I need an address. So we use something called ROM, read-only memory. This means that once it's created, you instantiate it to a specific value and it stays there. 3610 will go into how do we create that initial value. We don't have to worry about that yet. We'll worry about pulling out of memory. This is where decoders come in handy. So first, I want to use an analogy to help you understand what read-only memory is. It's like a neighborhood, and each house has a giant pile of packets or boxes, and you tell the mailman, I want you to go to house at 1000 North 500 East, right? That's how we kind of do this in Utah, right? We have the north-south grid. And then the mailman would go to that house, pick up the packet, pull it out and say, oh, this one has a 1 in it, right? Or this one has a 0 in it. So that's all it is. It's giving an address to go somewhere to look up what is in the packet, what is stored here. So the way that decoding works, the address, is we'll have a decoder that's going to take an address and let's deal with just 4 rows of this. So the precision, this is a word you'll hear a lot. The precision of this sine wave I'm saying is 6 bits. So it's accurate to 6 bits of data. That gets stored on, I'll do this down here first, in the rows. So this is row 0, and this is column 0. So I'm going to call this bit, this packet, this address, bit 00, B00. Now that bit can be a 0 or a 1, but its address is 00. 0 north, 0 east, main and center, right? Now, if I go down the column, it's bit 01, bit 02, and so on and then the row is bit, wait. Bit 0, 20, bit 30. Okay, and so on and so forth. Now, what I want is if I give an address, I want the entire row because I'm looking for the voltage that I'm going to output. So if I say, hey, give me row 1, then it's going to give me an array output of bits B00 to B50, right? Okay, so that's what I want my decoder to do. Now I'm going to start by saying this is not, what I'm about to build up here on the circuit is not necessarily what you're really going to do in ROM modern architectures. There are more efficient ways to build this, but this will give you an idea of what happens. So let's take bit 00 and bit 10 and say that I want to access those at some output. Well, this, I already said, is giving me 1 hot outputs. Well, I know that one and only one of those outputs is ever going to be true. So what I can do is set up a couple AND gates. So now I'm taking, this is just saying, if my address is seen and that bit is a 1, I'm going to output a 1. If my address is seen and the bit that I've stored is a 0, there's 0. So this output is the value of whatever the address tells it to be. Well, for this sake, I'll bring this around, bring this around. Okay, so now all of those have that true. So if the address is 00, this line is hot, 1 hot. These two AND gates then output whatever the bit is in 00 and 10. Is everyone clear on that so far? Okay, so what we want to avoid is what we call multiple drivers. We don't want it to freak out and say, oh my goodness, we could run into a situation where there's multiple drivers. Now, we know that that's not possible, right? Because we know that we designed this to be 1 hot, and so we could probably just hook these AND gates together and call it good, except for the fact that they're AND gates, and this one could be outputting a 0, and this is outputting a 1, and now we broke it, right? Because infinite current happens because you have 1, 1 here, a 0 here, there's no resistance between them. It's just both of them are going to throw as much as they can at it, and they're going to break. So we combine them with an OR gate. And ditto for this. And now I'm going to have a bit vector, I'll just call it V0, V1. So now my output is the result of the address lookup. So it's going to look up the contents of this entire row based on this 1 hot decoder. And I can use V0 and V1. And 2, 3, 4, 5, right? Because it's a 6-bit, I just didn't draw the rest. So that's a real world application of decoders. And that's also addressable memory. Given an address, get the entire row of data, the vector. Now, you could build a more complicated circuit that you can look up individual bits one at a time. Generally, we care about row decoding. It's kind of more efficient. Okay. We have time, we'll come back to a real world application of muxes that's kind of interesting. But for now, I'm going to move on to encoders. So encoders are the opposite of decoders, where they have, before we had n to 2 to the n, now we're going to have 2 to the n to n encoding. Encoding, decoding. Okay. And I have to change this, sorry. So decoders go n to 2 to the n, sorry, decoders, encoders go 2 to the n to n. We're going to draw it essentially the same way with a block. We're going to call it E for encode, and it's going to have, we're going to go 4 to 2 because it's easy for me to draw. Let me call them A, B, C, D just for ease. And it's going to output my encoded address, F0 and F1. So my outputs, F0, F1, are, well, if I have A, 0, if A is 1, then I'm going to have, sorry, I'm going to flip this around too so it follows F1, F0, flipped around. Okay, so 1 hot inputs, meaning 1 and only 1 is high. 0, 0, 0, 0 is nonsense. So these are my 4 possible 1 hot encodings. And the outputs are 0, 0, 0, 1, 1, 0, 1, 1. That's all an encoder is doing. It's undoing whatever the input is. Now, in the case of both encoding and decoding, your output F could be stored as binary, as I've written it here, or gray code, right? So gray code being the counting process wherein only 1 bit changes at a time, right? That's what we did with K-maps, right? Where we were utilizing gray code to ensure logic adjacency. We wanted to make sure that they were adjacent to each other. Well, this is binary. I could recode this into gray code, right? So there. But what if I didn't have that? What if I had an encoder that generated binary, and then I wanted an output of gray code? Well, that brings us to our next device, which is just code converters. So a lot of people like to think they switch encoder and code converters. So encoders are strictly 1 hot to an address, and code converters are transitioning from one type of code to the other. So for example, gray code to binary. So let's say that we have a truth table, and it's going to have so that's my binary input. It wants to create a gray code output. Well, we can design the circuit, right? We know how to do this. It's just going to be complicated because I have 4 inputs and 4 outputs. So for each one of the outputs, E, F, G, and H, I need a circuit, right? And each one of those is going to be built using a 4-input K-map. I'm going to give you the start of this. It's likely that I end up assigning this as homework, so I won't do the whole thing. But in gray code, nothing changes in the first row or the second row. But in the third row, I have 1, 1, just like we do in the K-map, right? Gray code. And then fourth row, again, I can only change 1 bit. So I'm going to go ahead and change that last bit, just like we do in gray code. And then keep counting 0, 1, 1, 0. Okay, there we go. Right? So then I can fill in the K-map for E, K-map for F, K-map for G, K-map for H, and build a circuit off of this truth table. That is a code converter. This is the beginnings of how I would design a circuit to convert from binary to gray code. Now, realistically, someone's probably posted some solution somewhere of the optimal way of doing this, and there's probably some clever things. But I think this functions well as an easy example, right? We've encountered code converters before. I just haven't called them that. Before we were doing BCD, right? Binary coded decimal to a 7-segment display, right? Where I was taking 4 bits of the binary code converter so that I could display them on an alarm clock style LED display, right? That was one of the examples I did before the exam. That's an example of a code converter. We could also do just straight binary to 7-segment. We could also do gray to 7-segment, right? We could convert codes all sorts of ways. We do it the same. Write out the truth table, fill in the K-map, do the simplification, build the circuit. Okay. Plenty of time, which is good. So now I've talked about gray code, I've talked about muxes. Let's talk about a real world example using muxes and gray code. So I am, by training and profession, what they call a mixed signal engineer. So mixed signal engineers use both digital and analog circuits. Now, digital and analog circuits don't play well together because they have fundamentally different things going on. So in research, I have 2 students working on right now for their senior projects. I'm building a neural recording circuit. The way we build neural recording circuits is you put, so I'm interested in rodent neural physiology. So I build electrode arrays, which is a bunch of pointy metal essentially, and stick them in rat brains. Now, to learn very much about the rat brains, you need thousands of electrodes. But you don't want to build thousands of recording circuits. So what you do is you have, say, let's start with 4 electrodes. You take a mux, you hook those electrodes up to a mux, and you hook the output up to, and I'm just going to call this a block with an R for record. So now I can record any one of those 4 by just changing my mux channel, right? Same thing we've talked about using muxes before. It's just kind of in an analog sense, and it saves me a whole bunch of circuitry. But gray code actually turns out to be the right way, so to speak, of doing this, because using binary has an issue. So we talked before about it takes work to change a gate, right? These have gates in them. And I said I wanted 1,000 channels, right? So let's say I have, or thousands of channels. Let's say I have 8 bits of mux select. And at my truth table, I have a whole bunch of rows because it's 8 bits. I'm not going to write them all. to 111. And I want to step through and go measure this channel, then that channel, then that channel, right? Because I need to measure all of the channels, record them. But what happens is I want to do this quickly. I don't want to spend 5 minutes recording this one, 5 minutes recording that one. I'm just going to go and kind of look at this one real quick and look at this one real quick and bounce through. Because it turns out digital circuits are way faster than brains, like way, way faster than brain. So there's no reason to wait. So I'll just kind of bounce around. But let's say the waveform, the brain has a signal that's a sinusoid. Nonsense, but let's say. What happens, because it takes so much work to change 8 bits, is when I change, let's say I change right here to go look at a different channel, instead of having a nice smooth, it goes, ooh, and does something weird. It kind of wiggles all over the place. Now, you'll learn more about the physics of why that happens, but basically it's called charge injection. And that's a problem. It ruins the recording because it's going from all ones to all zeros, and it just has to do all this work at once. And you may have seen this type of phenomenon in your desktop measurements already in the lab, where if you've hooked up the circuit wrong and you end up with something like VCC to ground, so power to ground, with nothing in between. Then your power supply, you're looking at it and going, huh, it says 2.5 volts, but I've told it to be 5. Well, what's happening is it doesn't have enough current. It can't supply enough current in order to maintain the voltage that you set it at. The same problem can happen. Gray code can fix that if in this circuit, because it reduces, it makes it so that only 1 bit ever changes, right? That's the logic adjacency. We save exactly 1 bit. We don't have the issue, and I never get these massive spikes. Instead, I get these little tiny ones that are pretty easy to deal with. So there's a real world example of both muxes and gray code, why we would use them. All right. Last section for today. We got plenty of time. This is good. I'm just going to go over some VHDL for these combinational devices. Now, most of you don't have laptops in front of you. That's okay. Mostly what I want to establish here is that these tools exist in VHDL. I don't expect you to like memorize the syntax and function of them yet, but I want you to know that they exist so that you can go look them up. So the first one that I'll use, I'm going to draw out all of the code for. And the first one is what we call a select statement. Now, I don't think I used this one to build one of the muxes, but you can really easily. So let's say we build a mux. Right, so create the entity. That's how we always start. The entity mux has these ports, A, B, C, they're standard logic, and an output F, which is also standard logic. And then I need the architecture. I'm going to call it B. Right, it creates behavioral. I'm going to keep it short. B of mux, this is usually created for you, is begin. And we know what a mux does, right? Is it's going to, based on C, which is going to be our select, it's going to assign F to be either A or B. So this case, we say with C select. So select is a keyword. We can't use that for like a port because that would confuse it. So I'm just going to use C. I'll write this out so I don't ruin it while I talk. Okay, so I will preface this by saying I have posted all of my today's notes to the same files on Canvas files notes folder. I think it's called Lecture 10-Combinational Devices, I think is what it's called. Then we'll have all of this code on here, so you can just go look it up. Anyways, what this is saying is with C, select what is F. So F is A when C is 0, and F is B when others. Now, others is a keyword. I could write, and probably should write, when 1, and then add another line that lets me know if something goes wrong. Because remember, C is standard logic, which means it's not binary. It's not just bits. It's a 0 or 1, or H for high, L for low, Z for high impedance, right? It has 9 different possible values. So what that was saying is it's going to assign B if C was equal to Z, which gets hard to troubleshoot. So we're going to say Z when others. That way, if something goes weird with my C signal in my testing, my output doesn't go to B, it goes to Z. And that's a good indicator that, oh, something weird happened, right? It shouldn't go Z unless something happened with Z. Helps you debug. Alternatively, we could replace this statement with the following. So this is just, we're just going to call this a conditional assignment. So this is just saying F is A when C is 0, otherwise B. Well, that has the same potential problem with C, right? So remember, this equal means it's a comparison. It's asking the question, is C equal to 0, right? Whereas this equal is the assignment statement. So if C is 0, it gets A into F. But if C is Z or X, it gets B. We can fix that with more else statements, totally fine, works great. I've done a case statement before. I'm not going to cover that today in class. You can go look up that again in the files notes folder. You can also do multivariable conditional assignments that would look something like, I'm going to write the code and then walk through it. Okay, so let's say I want to build a priority encoder, right? Which is like the encoder, but instead of having to have one hot inputs, I can accept I'll just draw the truth table. It's a little easier. It cares about where the first one is and doesn't care what the rest is doing. So B, this is a priority encoder truth table. So it's very abbreviated because the inputs have don't cares, right? So what it's saying is this is multiple rows of the truth table because this is 0, 0, 1, 1 and 0, 0, 1, 0. This is 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, right? So they represent multiple lines because I don't care what happens to the inputs as long as I know where the first one is. Where is the most significant one? That's what a priority encoder does. All right, well, we could build some weird complicated circuits to do this, but fortunately we have VHDL as a tool. So what I'm going to have is I'm going to have my output be called, I'm going to redraw this just so it makes sense. This is going to be W3, W2, W1, W0, and I have an output Y0, sorry, Y1, Y0. Okay, so when I have my most significant bit of W3, I want Y1, Y0 to be 1, 1. If my most significant one is at W2, 1, 0, 0, 1, 0, 0. Okay, in VHDL, this statement will do that because this says y is equal to y 1, 1 when w at 3, so this vector w that's 3 bits, is equal to 1. The first bit is 1, then y is equal to 1, 1. Notice the quotes instead of the apostrophe because it's a vector instead of just a single bit. And now it doesn't pay any attention to the rest of this assignment statement because this else. This says if this isn't true, do something else. But if this is true, we stop. So that's the priority encoder. I don't have to worry about every line. I don't have to write all of the equations. I just say, in order, this is what I care about. Now, you'll see that same kind of logic being written in all sorts of circuits, right? Where your first this will say something like when enable equals 1, right? So if enable doesn't equal 1, just stop, right? We don't want to do any computation if we're not on, so just stop. So this kind of ordered conditional assignment can be very useful to simplify logic. Now, another reason that we use the conditional assignment on the priority encoder, we like priority encoders, is because these don't cares, while hard to design and logic for yourself unless you're writing VHDL code, is actually really easy to design whatever's upstream from it, right? So something is passing at these inputs, and if those outputs could have all these don't cares in it, it's very happy because don't cares in a K-map mean it's easier to simplify, right? So that's what the priority encoder does for us over a regular encoder, is because it just doesn't care what's happening in this. Whereas a regular encoder would need zeros at those locations. So it simplifies the upstream logic a whole bunch for us. Okay, that's all I had for today. That's 10 minutes early, that's not too bad. I'll hang around and answer questions if you guys have any. And again, this code is posted to Canvas, so you can go look at it. It's a little neater than my handwriting. And then next week, we'll be doing a full adder VHDL in the lab, which I think is really where people will really start to get VHDL.
And the whole lab is in VHDL, right?
Yeah. Yeah, so bring the little packet things that I gave you, and I'm just going to collect them back. The little ICs and the resistors, so we don't need those. We're going to be VHDL for the rest of the semester. Yes.
It's a little late. Did we say when the test will be graded?
Yeah, I will have it graded within 1 week of when you guys take it, my usual. So Tuesday, I'll talk about the exam on Tuesday, as well as whatever class content. And then I'll get your homeworks graded by the end of next week is my target. So I intend to get fully caught up on grading by the end of next week. Okay.